Good evening, everybody, and welcome to another Astronomy on Tap. So, if you're unfamiliar with Astronomy on Tap, it's basically where a bunch of people gather together to talk about the latest and greatest in astronomy and in science and in technology while enjoying a nice beverage. My personal beverage of choice is a nice Coke. So, if there's a beverage of choice you would prefer while listening to an amazing presentation, be free to grab it and let us know what your favorite beverage is. So tonight we have the wonderful Dr. Jeffrey Bennett with us, and he has a PhD in astrophysics from the University of Colorado at Boulder. He specializes in mathematics and science education. In fact, he's been here in San Antonio a couple of times and was gallivanting to a lot of schools because all the kids wanted to hear from him. And he is also, one of his big projects is for the Totally by Big Kid Science, which is the free app, including he's also the author of the Max Goes to Insert Place Here. I think he's gone to the moon, he's gone to Mars, and where else has he gone?
Jupiter and the Space Station.
So it's an amazing kids book. If you haven't checked these out, if you have young space enthusiasts, check out these books. They are really fun and enjoyable to read. So, Dr. Bennett, the floor is yours. Please tell us about global warming and how it's demystified.
Thank you very much. So let me put up my screen for you. And I assume you can now see the first slide. Yes, good. So what we're going to talk about this evening is I've been focusing quite a bit on global warming in my career lately, but also throughout my career. I actually first started teaching about this topic back in 1982 when I was teaching my first astronomy course and realized how important global warming was as a topic in astronomy. And I think you'll see that and why it's part of Astronomy on Tap as we move along tonight. So Global Warming Demystified is the title of my talk. The subtitle you can see is answering your questions about the science, the consequences, and the solutions. So I'm going to very quickly take you through an overview of the science, the consequences, and the solutions tonight. And then we hopefully will have lots of time for Q&A. This topic, I started doing this talk a few years ago and quickly realized that if I was going to go through it quickly, I wouldn't be able to get to everything that you might have questions about that I should be answering. And so I ended up writing a whole book on it, and you can find that book posted freely online at globalwarmingprimer.com. You can also purchase copies if you want, but it is all posted for free there. And so if you go to that link, if there's any questions I don't get to tonight, and I'll refer you in a few cases to it, you will almost certainly find, because the book is in Q&A form, the answers to your questions there. So with that, we'll get started right into it. And I want to start this topic by asking the question, what is the future? And in the context of global warming, what is the future? So I might ask you, if I say, what is the future? What are you thinking about right now? When I say future, are you thinking, short term, long term? What comes to mind? For example, since this is an Astronomy on Tap talk, you might be thinking about a short-term future of all the exciting science that we're going to be getting back from Perseverance on Mars and the little helicopter right there. But I want you to think about it more generally. And when I ask this question, what I often find is if I say, hey, what are you thinking about when I said, what is the future? It'll depend on who I'm talking to. If I'm talking to, say, middle school kids, they'll probably be thinking about high school. If I'm talking to high school kids, they'll probably be thinking about college. College kids may be thinking about their first job. If you think about global warming, you might think in terms of what we hear about in the media. And if you watch the media reports on global warming, you'll usually hear talk about what might happen or what we should do by 2030 or by 2050. But I want you to change your perspective a little bit here and start thinking about the kids who are in school today, which may be your kids, your grandkids, depending on your age. Maybe you're in school yourself. I don't know who all is listening to me tonight. But if you think about kids who are in school today, Even a lot of the college students today were born after the turn of the millennium, after the year 2000. Well, right now, average life expectancy is about 80 years, but given the advances in medical science and health that we can expect to be coming this century, it's very likely that by the end of the century, the average lifespan will be well over 100 years, which means most of today's kids, your grandkids, will still be alive in the year 2100. And so when we talk about the future in terms of global warming, I think it's important to go well beyond these 2030, 2050 dates and start thinking about the year 2100 and beyond. And if you excuse me for 10 seconds, I have to close a door. Thank you. I bet if we were at a real bar, I wouldn't have to worry about somebody starting to mow the lawn outside, but so be it with Zoom. So with that background, just to keep that in your head about the year 2100 and beyond, let's get into now the first of the three parts: science, consequences, and solutions. So we're going to be talking about the science of global warming. It's also known as climate change. As far as I'm concerned, the two terms are basically interchangeable. There is a subtle difference I might address later, but names. And to start the science of this topic, we want to start with astronomy, because it turns out this is really the root origin of much of what we understand about it today. So we'll start with what I like to call a tale of two planets. So what you see here on the screen is Earth and Venus, and you see them to scale. And what you notice about them is they are essentially the same size. Both planets are the same size. Moreover, from data that we have from spacecraft and other studies, if we were to slice them open, we would find that these two planets look very much the same inside, similar layering, similar composition, and so on. In fact, if you think about them in the context of all possible planets, these two planets, Earth and Venus, are about as close to being identical twin planets as it's possible to be. The only major difference between them is in their global average surface temperatures. On Earth, we have this very pleasant global average surface temperature. On Venus, it's extremely hot, so hot that lead melts on its surface, hotter than a pizza oven here on Earth. And so one of the things I want you to do when you're learning or hearing about the science of global warming, or talking to others about the science of global warming, is ask people to think like a scientist. And if you're thinking like a scientist, you would look at this and look for the mystery. And the mystery is pretty clear. Why would two planets that are in most other respects essentially identical twins still have this one major difference between them? And so when you think about that question scientifically, well, you know what we do in science is we begin by hypothesizing, by coming up with a possible explanation that we can then test. And in this case, the possible explanation that almost everyone comes up with first is that maybe the reason Venus is so hot is because it's closer to the sun, which sounds reasonable at first, but if you test it out, you'll find it doesn't work. The distance alone cannot explain this extreme temperature difference between these two planets. You can actually calculate it out if you want, but you can actually see it very clearly if you use a scale model of the solar system, like the Voyage scale model solar system here in Washington, D.C. There's the National Air and Space Museum. If you've been up there, you may have seen this. There's also one outside the Space Center Houston, a little closer to you down there in San Antonio. And I'm hoping maybe someone there will want to bring one of these to San Antonio. We're working on spreading them around the country. If you're interested, contact me and I'll help you figure out how you can get one there in San Antonio. But what we've done is we built the solar system at a scale of 1 to 10 billion. So that right there is the sun at 1/10 billionth of actual size, which makes it about that big. On that same scale, Earth and Venus are both smaller than the ballpoint in a pen, so really tiny, and they're located in the glass discs over here. And here you can also see the relative distances. And what you'll notice when you just think about it qualitatively is, imagine that we built a big bonfire here where the sun is located, and then you walk over to Venus and Earth. Well, of course, it's going to be a little warmer at Venus because you're a little closer, but you can probably tell that that difference is not going to be enough to explain this huge difference in temperatures. So if it's not distance, what is the explanation for this huge difference in temperature? If we were in class, I might ask you to come up with other ideas and we would discuss them, but I'm just going to tell you the answer right now so we can move quickly. And the answer is the difference is attributable to what we call the greenhouse effect. And you're probably familiar with this, but just to basically review, we get energy from the sun in the form largely of visible sunlight that comes in. Some of it's reflected back to space. The rest is absorbed by the ground and the oceans here on Earth. And then the ground and the oceans have to return that energy back to space, and they do so in the form of infrared light, represented by these red squiggly lines. And you'll notice these red squiggly lines, unlike the yellow visible light, they don't go straight back out to space. Instead, they take this circuitous path because the little blue dots represent what we call greenhouse molecules that absorb and then re-emit the infrared light, and they re-emit it in random directions. What are the blue dots? The greenhouse gas molecules. On Earth, the three major greenhouse gas molecules are water vapor, carbon dioxide, and methane. And you can see that the more blue dots you have, the harder it will be for this infrared light to escape. And the result is that the more greenhouse gas you have, the more heat you have added to your surface, oceans, and lower atmosphere. Now, that's a nice story I've just told you, but if you're not a scientist, and you're thinking like a scientist, you might say, well, how do you know that that's true? How do you know that the greenhouse effect really works the way you just showed us in that picture? And the answer is through evidence. And we have two lines of evidence for the greenhouse effect. The first is the evidence we can measure in the laboratory. In essence, what you do is you shine different wavelengths of light at tubes containing different types of gases, and you measure what happens. And these measurements are old science. They were first done in 1856 by a woman named Eunice Newton Foote. In fact, by 1896, the famous Swedish scientist Arrhenius had already learned enough about the greenhouse effect that he was able to calculate what would happen if we doubled the amount of CO2 in Earth's atmosphere. And the answer he got is virtually identical to the answer that our most sophisticated climate models give us today. So 150 years ago, we already had a pretty good understanding of the greenhouse effect. And this laboratory evidence tells us, yes, we understand how the greenhouse effect works. And the only remaining question is, does it work the same way in the real world as it does in the laboratory? And for that, we can look at actual planets, the planetary evidence. And so what we do there is we compare the predicted and actual temperatures of planets. And what we find is if we calculate for any planet or moon with an atmosphere in our solar system, if we calculate the predicted temperature without the greenhouse effect, we get the wrong answer. If we calculate it with the greenhouse effect, we get the right answer. And that validates what we've learned from the laboratory. And I want you to notice one thing on this particular slide, which is, sorry, let me go back here. This painting here from one of my children's books, The Wizard Who Saved the World, shows you the actual calculation without the greenhouse effect for Earth. And what you'll notice is that if we did not have a greenhouse effect on Earth, the temperature would be negative 16 degrees Celsius, which is below freezing. In other words, without a greenhouse effect, Earth would be too cold for life. And that brings us back to our tale of two planets. The reason our planet is livable is because we have enough carbon dioxide in our atmosphere to raise the temperature from below freezing to this comfortable temperature. In other words, the greenhouse effect is a very good thing for life on Earth. We would not be here without it. What's going on with Venus? Well, it turns out Venus has about 200,000 times as much carbon dioxide in its atmosphere as Earth does. So 200,000 times as many blue dots in that picture that I showed you before. And that enormous greenhouse effect is what makes Venus so incredibly hot on its surface. So you might think about it this way. If the greenhouse effect is a very good thing for life on Earth, Venus is absolute proof that it's possible to have too much of a good thing. And right there, we've just about finished the basic science of global warming, because you see how we know for sure that more carbon dioxide, more greenhouse gas means higher temperatures. You then take that and combine it with the fact that the carbon dioxide concentration in Earth's atmosphere is indeed rising, as you can see here on this graph showing measurements made since the late 1950s. The units here, parts per million, what this is telling you is that back in the 1950s, the amount of carbon dioxide in Earth's atmosphere was about 315 carbon dioxide molecules out of every 1 million molecules of air. And you can see that has risen dramatically from 315 to now above 415 parts per million. And the only question remaining here, you might wonder, well, what about before 1958? And you might think, well, that's going to be hard to know about the past carbon dioxide concentrations, since no one was measuring it until this time. But it turns out there's a lot of ways we can figure out what the carbon dioxide concentration was further in the past. Some of the most reliable data come from ice cores, where scientists drill down into the ice and bring up this layered ice, which represents snow that fell over time in the past. And remarkably, if you count down the layers of snow, you find that the deepest ice core drill, which goes down about 2 miles into Antarctica's ice, is bringing up snow and ice that fell in Antarctica 800,000 years ago. And as a result of that, we have an 800,000-year record of Earth's carbon dioxide concentration. There were air bubbles trapped in that ice. You basically just go into each layer, count how far down it is in years, and that tells you then the carbon dioxide concentration at that time. And what you'll notice is that over that last 800,000 years, the carbon dioxide concentration varied from about 180 parts per million to 280 parts per million. It was 280 parts per million in the year 1750, which is roughly around the time we started burning a lot of fossil fuels. And since that time, it has shot upward to our current 415. And that's one of 4 different ways we know that the source of this extra carbon dioxide is human burning of fossil fuels and a few other activities, but that's the biggest one. If you want to know the other ways we know for sure that it's our carbon dioxide from fossil fuels and other sources, in the global warming primer that you'll find online, I go through all the other lines of evidence, but I'm not going to do that now. And you can see that this 415 parts per million today is about 45% higher than it was any other time in the past 800,000 years. And if you extrapolate this upward, we'll be at double the pre-industrial value, 560 parts per million, in only about 50 years, well before that year 2100 that I told you to keep in your mind. And we'll be approaching triple that value by the middle of the next century, and so on, if we keep going the way we are today. And that brings me to the summary of global warming science, which we can summarize in 3 simple steps that I just call global warming 1, 2, 3. Number 1 is, it's a fact that carbon dioxide makes Earth warmer than it would be otherwise. This is an indisputable scientific fact, measured in the laboratory, validated on planets, as we've talked about already. Number 2, it's also a fact from those graphs that I've shown you that our human use of fossil fuels, coal, oil, and gas, is adding more carbon dioxide to the atmosphere. And if you think about those 2 facts, more carbon dioxide means warmer temperatures, and we're in fact adding more to the atmosphere. Number 3 is pretty obvious. It is going to get warmer. And that right there is all there is to the basics of global warming. When you hear people tell you, oh, global warming is really complex, the climate's really complex. Well, the climate is complex, but the basic idea of global warming is very simple. It's just this 1, 2, 3. And the measurements show that it's happening just like we know it should, according to that 1, 2, 3 science. This is a graph showing you global average temperatures going back to 1880, which is about as far back as our reliable temperature records go, and the trend upward is quite clear. If I remember what I have on my next slide correctly, this is where I ask the audience a quiz question. I won't be able to hear your responses, but here's what I usually like you to think about is, if global warming science is so simple, as I've just explained to you, 1, 2, 3, why do so many politicians have so much trouble understanding it? That part's not the quiz question. That's too hard to answer. I don't know why politicians have so much trouble with it. Here's the quiz question. Who was the first major global leader to recognize this 1, 2, 3 science and speak out about it on the international stage for everyone to pay attention to? And now that you've thought about who you think the answer would be, here's the actual answer. It was British Prime Minister Margaret Thatcher in 1989 when she gave a speech to the United Nations. And look at what she said. What we are now doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways. And you could see that's just Margaret Thatcher's restatement in her own words of what I've described to you as the 1, 2, 3 science of global warming. You'll notice she's very clear about it. There's no ambiguity. It is us. It is damaging. It is something we must change. You can actually watch the whole video of her speech. I have a link to it on the globalwarmingprimer.com website. It's actually very interesting, the full speech. Excuse me. And I want to just pause here. For those of you who I remember who Margaret Thatcher was, she's considered to be one of the founders of modern conservatism, along with Ronald Reagan. And so if you ever hear anybody tell you that global warming is some sort of a political idea, liberal idea, or something like that, point back to this quote and show them that the first global leader to call attention to this on the global stage was one of the founders of modern conservatism. In my Global Warming Primer Online, I next go through a set of skeptic claims and how we can understand what the actual truth is behind them. We're not going to do that here tonight because we don't have enough time, but I just want to call your attention to 2 very common skeptic claims. Again, go to globalwarmingprimer.com and you can read all about all of the common skeptic claims there. But here, one of the common ones you might hear is people saying it's the sun. Maybe it's the sun. Well, it's not the sun. You can tell here because while the sun and global temperatures tracked together for a while, in the last few decades, the sun's been staying stable or going down in intensity. Temperatures have kept going up. That rules out the sun as a possibility. Another thing you might hear is, well, the climate changes naturally, so why worry now? And in fact, the climate does change naturally. This graph, I'm showing you the same in blue there, the same carbon dioxide data for the past 800,000 years that I showed you before, but now I've overlaid it with a red curve, which represents the temperature during that time. And here's the amount of temperature changes. You know, notice these are big changes, 18 degrees Fahrenheit, 9 degrees Fahrenheit. And that explains why every time we're in one of these dips in the last 800,000 years, it's what we call an ice age. And in between, we have the warmer interglacial periods. You'll notice we're in an interglacial warm period right now. But here's why you should be concerned. Because first of all, you'll notice they go together. Why? That's just the 1, 2, 3 science again. The carbon dioxide and the temperature go hand in hand because that's the way what the science says they should be doing. But there's always a lag time in the temperature response. And you'll notice we're already at fairly warm temperatures. The carbon dioxide has shot up, which should make us very concerned that the temperature is going to shoot up in an equally dramatic way. And so if you hear people say, well, there's nothing to worry about. Well, actually, there is something to worry about based on the past data. If you hear people say, well, the climate models can't be trusted. Well, this is not a model. This is the actual data here. In fact, the climate models tell us there are some feedbacks that will make the actual temperature increase probably less steep than what we see here. But the fact that this should give us great cause for concern is very clear. The second part of my talk, consequences of global warming. I'm going to move very fast through this because in a lot of ways it follows very simply from the science. The first is regional climate change. And I mentioned before, I would tell you a little bit of the subtle difference between the terms global warming and climate change. Global warming usually refers to the average temperature of the Earth increasing. Climate change refers to the fact that different places have their climate changing by different amounts. And I want to show you this quick little video from NASA, which shows you how temperatures around the world compare to their 20th century averages. Blue is colder than their average, red is warmer than their average. And as I play the video here, you can see the years going by, and you can see different places at different times might have been warmer or cooler than their 20th century average. And for the first few decades of this video, there's no real obvious pattern. But keep watching. And you notice in the last few decades, the pattern has become very clear. The entire Earth virtually is warming up with a couple of exceptions, and some places warming much more than others, particularly up in the Arctic. That has lots of effects. One effect is that we get more summer days. This shows you the distribution of summertime temperatures from 1951 to 1980, all normalized on a bell curve. And this shows you what has happened in the last just a little over a decade ago. And you'll notice that the whole curve shift to the right. And that's something I'm sure you've noticed in San Antonio. There are a lot more days. In fact, the days that we used to call hot a few decades ago are kind of our new normal. And there's a lot more that we call extremely hot in the summertime than we used to have. A second major impact of global warming is we get an increase in storms and extreme weather. You might wonder, why do those two things go together? Think back to what I told you about what the greenhouse effect does. It's trapping heat. Heat is a form of energy. We're getting more energy in the lower atmosphere and ocean. What causes storms? What drives storms? Heat and energy. Therefore, as we get more heat and energy in the oceans and lower atmosphere, we're going to get an increase in storms and extreme weather, more extreme hurricanes, more wildfires in dry areas. And this graph shows you the total number of extreme weather events taking place. I won't go into detail, but you can see very clearly, yes, it is an upward trend, just as we expect. The third major consequence of global warming is melting of Arctic sea ice. Remember, I showed you the Arctic is warming more than other regions, and that's having dramatic effects that are causing us to have less ice in the Arctic. Here's a comparison of the ice cover in 2012 to a couple earlier years. Here's the all data graph, and you can see 2012 was a particularly low ice year, but the trend is overall clearly downward. And that has a couple of other effects. You might think, well, melting sea ice, that's good. We'll be able to sail ships across the Arctic. But it has some very serious consequences. In particular, ice reflects a lot of sunlight. Water absorbs much more of that sunlight. And that means that as ice melts, this effect tends to amplify all the other carbon dioxide related effects of global warming. So it's a very serious consequence for us. It's also been tied to changes in the jet stream, the polar vortex, which it probably explains some of the very weird weather we've experienced in winters in the United States in the last few years. The fourth major consequence is that we get a rise in sea level. And the rise in sea level occurs for two reasons. One, as the temperatures warm, ocean water actually expands a bit. That's already caused the sea level to rise by about a foot in the past 100 years or so, and will almost certainly cause another foot or so of sea level rise in the rest of this century. But on top of that rise, we get a rise from the melting of glacial ice into the oceans. The Arctic ice is floating in the oceans, so it doesn't affect sea level as it melts. But ice in Antarctica, Greenland, mountain glaciers, as that melts and flows into the oceans, it will cause sea level to rise. And most scientists are guessing that we don't understand the rate of melt super well, so that's why it's more guesswork. But the common guess is that we'll get about 3 feet a meter of sea level rise by the end of this century, that year 2100 again, when our kids and grandkids will still be alive, which means these red areas will be flooded. And you can notice that's got a big effect on areas near you. It's worth noting that if we don't reverse this trend, eventually all that ice will melt, probably not for at least a couple thousand years. But if that happened, sea level would rise by more than 200 feet, which I think means San Antonio would be underwater. And the fifth major consequence of global warming, the one you hear the least about, but it's just as important as all the others, is ocean acidification. Some of that carbon dioxide going into the atmospheres, dissolving in the oceans, where it turns into an acid that has effects on coral reefs, on sea life, on our food supply from the oceans, and so on. At this point, if you've been paying close attention, you might feel much like what Greta Thunberg here said, because this is scary. The warming is occurring. It's going to continue to occur as long as we continue to do what we've been doing. And the consequences are real and very severe, and could be enormously severe by the year 2100. And that's why she says this. I want you to panic. I want you to feel the fear I feel every day. But notice she doesn't stop there. She concludes with, and then I want you to act. And the reason she wants you to act, the reason we all want all of us to act, is because as scary and serious as this problem is, we know how to solve it. And therefore, I want to focus the last part of my talk on these solutions. What is the solution? Well, we already have the existing technology to solve it, because the solution is really very simple. Most of the problem is being caused by our burning of fossil fuels. So if we can convert to other energy sources, the problem is solved. And we have three basic technologies that will allow us, in principle, to stop using fossil fuels with no negative impact on our lifestyle, because we'd have just as much energy to use for benefits. The first is energy efficiency, which allows us to get the same benefits with less total energy use and cost. The second is renewables like wind and solar. And the third is nuclear power, which I know lots of people have lots of opinions on that, but whatever your opinions are, and we could talk about that during the Q&A if you wish, it does not emit greenhouse gases. So in terms of global warming, nuclear power is one of our potential solutions. Beyond those existing technologies, we have a lot of technologies coming down the line that people are working on. For example, carbon neutral biofuels, which could be used for current airplanes and ships. So when you hear people talk about the damage from flying, well, that has a solution. So use these carbon neutral biofuels instead of current fossil fuels for our jet fuel. Solar energy from space. You put your solar panels up in space where it's never dark and never cloudy, beam the energy down to Earth. Nuclear fusion, which is a technology we don't yet have, but people are working on, which uses hydrogen at its fuel and is so powerful that if we hooked up, in principle, a nuclear fusion reactor to just one person's kitchen sink, and turned on the water and pulled the hydrogen out of the water and fused it, that alone could power the entire United States. It's an incredible energy source if and when we learn how to tap it. And much more. We could even imagine, and people are working on technologies to pull carbon dioxide back out of the atmosphere so that instead of our current 415 parts per million, we could actually bring it back down to something that would probably be safer for the future, like 350 parts per million. So why aren't we doing it? If we have existing technologies and more technologies coming down the line, what's stopping us from solving this problem right now? This is the part of the talk where I start expressing opinions. I would argue that everything I've told you up to now is an indisputable scientific fact, but now I'm going to talk about opinions. I believe what's stopping us are the socialized costs of fossil fuels. We do not pay when we go to buy gas or oil or coal. We don't pay their full costs. Instead, those costs get distributed over society. For example, the health cost of air and water pollution, the defense cost of protecting our oil supply, subsidies and tax write-offs, the costs associated with terrorists and totalitarian and governments that have been fueled by oil revenue and so on. In fact, the IMF estimates, and several other groups have estimated, that we subsidize fossil fuels to the tune of $1 trillion a year in the United States, 4 trillion globally, which means if we were paying that cost, we would find that fossil fuels, instead of being cheaper than those alternatives, as they seem to be when you go to buy them now, they're in fact several times as expensive. Which means the obvious solution to this problem, again, we're in the opinion-based part of my talk, is put on a carbon tax that accounts for those socialized costs. If we did that, we would find no one would buy fossil fuels anymore because they're more expensive than the alternatives. And I'd love to talk more about this. Maybe in the questions you can ask me about the Citizens Climate Lobby plan if you're not familiar with it, but that's my personal favorite plan, or the plan proposed by a group of former Republican presidential administrators that they call the conservative case for carbon dividends, which is essentially the same as the Citizens Climate Lobby plan. But I want to conclude by taking us back to what I started with, but instead of a tale of two planets, this time it's a tale of two futures on one planet. If we keep going the way that we are now, I think I've convinced you that we face an existential threat to our civilization. I want to be sure I'm clear about what words I'm using here. I'm not saying we're going to kill off life on Earth. That won't happen. I'm not saying we're going to drive ourselves to extinction. I don't think that can happen. What does have the threat of extinction is the level of prosperity and civilization that we all enjoy today. We will not be able to keep living the way we do if we keep going as we are today. But if we switch, if we make a rapid transition to something that doesn't continue to increase carbon dioxide in the atmosphere, and then we start introducing the new energy sources I talked to you about that can give us much more energy in the future, and we use that to start removing carbon dioxide from the atmosphere to bring the level back down to something better, you can imagine a world by the year 2100, right? Again, our kids' and grandkids' future, when we're in what you might call a post-global warming world, because not only have we stopped global warming, but we've returned the climate back down to a much more stable state. And with that, we'd also have much more energy at lower cost without pollution, which means you could imagine a world by the year 2100 where we could have eliminated global poverty, eliminated problems with fresh water because we simply desalinate ocean water, eliminated the environmental damage of mining around the Earth because we don't mine on Earth anymore. We instead go get it from the moon, and so much more. There is truly an incredible world awaiting our kids and grandkids during their lifetimes if we act quickly and dramatically today. You can read this cartoon if you want really quickly. I'm not going to spend any time on it because I'm just about at my time limit already. But I want you to personalize this idea. If you're an adult today, maybe the year 2100 isn't in your future, but it's in your kids' and grandkids' future. So I want you to think about writing a letter to your grandchildren based on what you've heard today. And so you're going to take this letter, you're going to seal it in a time capsule for 50 years. Why 50 years? Because if you look at the typical 25-year spacing of generations, in 50 years, your grandchildren, whatever age you are, your grandchildren will be roughly your age at that time, 50 years from now. So if you're currently retired, your grandchildren will be retired in 50 years. If you're currently a college student, your future grandchildren will be college students in 50 years, and so on. So here's what I want you to write. Dear grandchildren, as I write this in 2021, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I have examined the evidence, and I have decided to, and then you write in what you're gonna do. Hope your world is a good one. Love, you. And one of the things I want you to take from this exercise is to think about what it means to our current politics. And here's how I want you to think about that. You probably hear that we are incredibly divided politically today. There's nothing that the left and the right agree on. Well, I'm going to tell you that's not quite true. No matter how bad you think the situation is, there's one thing that I will argue that everyone of any political belief agrees upon, and that is that all of us want a better world for our kids and for our grandkids. And therefore, I think that all of us, no matter what your political beliefs, if you think clearly about this and what you're going to write here when you fill in your decision and what it's going to mean to your grandchildren when they open this in 50 years, if you do that, then I think we will all come to agreement and find a solution to this problem. And I'll close with another conservative quote from Ronald Reagan. What is a conservative after all, but one who conserves, one who is committed to protecting and holding close the things by which we live? This is our patrimony. This is what we leave to our children. And our great moral responsibility is to leave it to them, either as we found it or better than we found it. Again, if you have questions remaining that we don't get to during the Q&A session, go to globalwarming.com. And you'll find, I think, the answers in my primer there. For kids, I have my book, The Wizard Who Saved the World. There you can see it being read from the International Space Station for the Storytime from Space program. For middle school kids, I have an entire curriculum on Earth and space science. It's posted free online, and you'll find the climate change chapter with that link. And that's all of my books. You can find them at bigkidscience.com, my kids' books, my books for the general public and college students, and the Totality app, which is free to download on your iPhone or Android phone. And we're updating it right now. It'll have the path for the 2023 annular eclipse and the 2024 eclipse, which goes right through San Antonio. If you download this app and tap on your location, it will show you how much totality you're going to get right there at your own house. So please download that, tell your friends about it. It's completely free. And I will stop. Thank you.
Thank you, Dr. Bennett. It's an amazing topic, and it's great to see all the evidence laid out, as well as just to hear from an expert on the topic. So now is an opportunity, folks, if you have questions for Dr. Bennett. Okay, it looks like we got our first one here. Is there any evidence of the oxidation of the drilled ice over those time frames that might affect the CO2 readings?
No. These have been very, very well studied and documented. The temperatures can be extracted from there. You would see, and these readings are done from air bubbles that are trapped in that ice. So if there was something going on in the ice, you would see it.
Okay. As the planetarium coordinator and somebody who works with kids a lot, so my question for you is, especially for our young viewers, especially since you encourage people, hey, you're writing a letter, what is some practical things that our young viewers can do now to help this problem along? Because I know for many young viewers, they're like, wow, this is a big problem. I don't know if I can tackle it by myself. So what are some simple yet practical ways that they can tackle it?
That is a great question. And so when I do speak on this to lots of middle school and high school groups, and obviously with them, I have to focus in a slightly different way. We all, as adults, we can take action right now. Write that letter to your grandchildren, talk to your politicians, support a solution like the Citizens Climate Lobby Plan for a carbon tax, and so on. For kids, they might feel like they're just sort of being hit by a problem we created that they're now stuck with. So I think what's really important is to focus on that positive future, what I call the post-global warming world. Kids need to understand this topic because it affects them, because they have influence with us, with their parents and their grandparents and their teachers. The movement that Greta Thunberg has started has really helped, I think, raise a lot of awareness, and lots of kids can do that. But kids should also be thinking about what they're going to be doing, what they want to do with their own lives. And no matter what career path they're interested in, there's a way to make it relevant to this topic. First, in helping us solve it. But second, I like to point out to kids that even if they're the person who comes up with the solution that solves the problem and then we're done with it, they're still going to be pretty young. They still got a lot of years left in their lives till the year 2100. What are they going to do after that? And so I want kids to be thinking about all the incredible possibilities that await us. What could we do with all that virtually unlimited energy from nuclear fusion? And you know, scientists have been talking about getting nuclear fusion for a long time and we still don't have it. But I'm pretty confident that by the year 2050 or 60 or 70, we're going to have it. And if it's not nuclear fusion, it'll be solar energy from space or something else incredible. We are going to have unlimited, cheap, clean energy available as long as we solve the problem of today first. So encourage kids to think about, you know, what planet do they want to visit before the year 2100? Because in principle, they'll all be accessible to us.
All right, our next question that's coming in is, would deforestation and increased use of fossil fuels outweigh population decline or increase as a urgent factor involving global warming?
So that's an excellent question. So there's a lot of different things going on in there. So first, fossil fuel burning is the #1 cause of global warming, but it's not 100% of it. It's more like at the 70, 80% level. Other causes are things like deforestation, because when you cut down forests, the tree or burn forests, the carbon dioxide that's been trapped in them gets released. So therefore, reforestation helps counter that by absorbing carbon dioxide from the atmosphere. Agriculture is another significant contributor in a number of different ways to global warming. When it comes to population, a couple things in that question. So population, the more people there are in general, the more carbon dioxide emissions we're going to have if we're using fossil fuels. However, different parts of the world use those fossil fuels at very different rates. So the average American is using many times as much fossil fuels as the average person in places in Africa, for example. So it depends on where the population is located. Also, I think the question might have pointed out something that's been in the news lately. There's been a lot of talk about population decline. You should be very careful in interpreting what you're hearing in that talk. Population is by no means declining. The rate of growth has been declining, but population is still increasing dramatically. There's virtually no scenario that I've seen where we don't add another 2 billion people in the rest of this century. And 2 billion people is, 6 times the population of the United States. If they all live the way we do, which we hope they do, that they have good lives, if they're getting that energy from fossil fuels, that would be horrible, right? That would be 6 times the emissions of the United States for those extra people. So population growth is still continuing. It's something we do need to get under control, but in the meantime, we have to make sure that all those people being added to the world are able to live at a good standard of living without doing tremendous damage to the planet. And that means, again, we need to make that transition to non-carbon emitting sources.
All right, next question. This is from Tracy Becker, who is the lead of Astronomy on Tap, and she says, excellent talk. And thanks for the very clear breakdown. And her question is, as many skeptics point out, models are not always accurate. Do you have an example or two that show how some of the predictions of the climate models are already coming true, validating those models?
I don't have the graph readily available here, but yes, there are graphs that show how the models line up with the predictions. And so when they do models, they always do a range, right? They have the low case, the intermediate case, and the high case. And what you find is that the models going back, if you look at like some of James Hansen's models from the 1980s, they've actually been tracking closer to the high case than to the intermediate case. But the models within their uncertainty ranges, they have been essentially perfect to date.
All right, next question. Auto companies have begun to shift to electric cars. Some argue that if we do not shift how electricity is generated, we are merely shifting carbon to another source. What is your perception on this?
So when you get an electric car, you're using electricity from the grid. So that is correct. Now the impact of that driving is going to depend on what's the source that produced that electricity. If you're getting that electricity from a coal plant, then it's still producing carbon dioxide emissions. However, as you may or may know, electric motors are much more efficient than gasoline motors. So typically, we would say that assuming you're getting it from a fossil fuel, electric cars have about triple the gas mileage of a corresponding electric car. So your typical electric car is getting the equivalent, even if they're getting the gas from fossil fuels, the energy from fossil fuels of 100 miles per gallon. So their total emissions are still going to be less. But even better is if that electricity is coming instead of from a coal or gas-fired plant, if it's instead coming from a nuclear power plant or a solar or a wind power plant. In that case, it's not producing any emissions at all. Or if you're charging your car at home with solar panels on your roof, it's not producing emissions at all. And one of the reasons we want to electrify cars is because it's much easier to get the energy in a clean way from electricity, since we have nuclear, wind, solar available, than it is to come up with a new gas that you pour into the car like we do now. Although you could, in principle, do that with what we call hydrogen fuel cells. So that's another possible car technology for the future.
Well, I know I've heard rumors that basically the amount of production that it takes to create an electric car with all the battery acid and everything is just as toxic as fossil fuel. So is this accurate, or is there any validity behind these claims?
So it's complicated behind that. So when you look at a car, you should look not only at how much energy and emissions are produced as you drive it, but also what we call the life cycle impacts of the car, which means everything from mining the materials that go into the car to what happens to the car after you're done with it, whether it gets recycled or thrown in the dump, right? And so that's where it gets complicated, right? If you're mining all those materials with big trucks that are burning fossil fuels, then you got a lot of emissions going into the air in the process. And so if you look at how electric cars are actually made today, according to the most recent analyses I've seen, we're just now starting to reach a break-even point on life cycle cost. However, the goal is what is sometimes called electrify everything. In other words, even those big mining trucks would be running on battery power, getting their electricity from nuclear or wind or solar. And if you do that, then you can make it emission-free throughout the whole process of making the electric car. That's clearly far better than any alternative. The second part of what you asked is the toxicity. So when you do that mining, you have a lot of metals in there that are toxic being used and being dug up and so on. So part of the answer there is, when you're done with your car or anything else, do you recycle all that material so that at some point in the future, we wouldn't be continuing to dig up these toxics, but we would always be recycling them? If we are, then in the future, you reach a point where it's all positive again. If not, it could be negative. One of the really interesting things there, nobody asked me about yet, is why I keep talking about nuclear power. Nuclear power is highly what we call energy intensive. It only takes a very small amount of nuclear fuel to produce a huge amount of energy. And depending on how you look at the analysis, and there's a lot of debate, scientific debate about this, it's possible, I'm not saying it's certain, but it's possible that nuclear energy may actually be greener than solar and wind when you factor in the effects of the mining for all the materials that go into solar and wind, because there is so much mining necessary in contrast to nuclear, which we can actually power mostly with existing nuclear supplies by basically taking our bombs and turning them into fuel, which would be a good thing also to dismantle all of our nuclear bombs. And then in the future, we should have these energy technologies where if we do need more metals, we go get them from the moon and don't keep digging up and toxifying the earth.
All right. Are there any other questions, folks? Well, Dr. Bennett, thank you so much for your time and for your wonderful presentation. Folks, be sure to check us at the Scobie Education Center on our Facebook page and Twitter, as well as our own website, because we have a lot of things going on for you young members in our audience. We do have our summer camps available, so be sure to check those out. And if you're interested in joining us for our virtual summer camps, please do sign up. And also check out our YouTube channel where we post videos weekly of a unique topic in space. So with that, cheers to the universe and have a wonderful night, folks.
Thank you very much.